This tutorial will go over a method on how to create a finite element model of a honeycomb sandwich panel with composite face sheets using Patran version 2012. Modeling the honeycomb cell geometry is possible, but it greatly increases computation time and will not be a plausible method for larger parts. This video will demonstrate how to model the honeycomb using solid elements and assigning a 3D anisotropic material to these elements. The face sheets will be modeled using shell elements and a 2D orthotropic material. Firstly, the material properties of the honeycomb which are used for this model will be the Nomex hexagonal core, and let's just choose this one that's in the blue squares. It is important to note that the working units for this model will be Newton millimeters. The important values for us will be the modulus values for the compression direction, which is parallel to the cell holes, and the L and W directions, L being the ribbon direction. Next, the composite material used for the face sheets will be the standard carbon fiber fabric or weave, shown here. We will need the Young's modulus or elastic modulus in both the 1,1 and 2,2 directions, as well as the major Poisson's ratio and the in-plane shear modulus G1,2. We will also need the out-of-plane shear modulus values for G1,3 and 2,3, which are equal. These values are not shown in this data sheet, but can be assumed to be less than the in-plane shear modulus, and for this example, we'll just use 3.5 gigapascals or 3,500 megapascals. Later in the video, I'll go over exactly how to create the material properties using Patran and where to input each of these values. Let's go ahead and get started with the model. Once Patran is open, create a new model file. I'm going to name this file HC panel tutorial. Let's click OK. Once the window opens, let's go ahead and just leave these as default. Next, I like to turn the background to black while I'm working on a model. Lastly, I'll turn off the auto extend feature just so when I'm increasing the model size, it doesn't automatically expand the window. Now we can start by creating the geometry, which we can mesh and assign the properties to. You can either use CAD software to create geometry, or if it's simple enough, as it is in our case, we can use the FEM software. Let's start by creating points for the corners of our panel. I'm going to turn on the point indicator so it's easier to see. You can see a turquoise circle pop up. So let's go ahead and make the panel 100 millimeters long. And extend so we can see it. And let's make it 25 wide. These are just arbitrary numbers. So we'll create the 4 for the bottom. This is with at 0 for the Z direction in the Z axis. And now let's give a panel thickness. Rotate so we can see. And let's go ahead and give a panel thickness of 10 millimeters. And now we're creating the points of where the upper face sheet will be. So again, at the same 4 locations as the bottom points, just with an offset of 10 millimeters for the actual thickness of the panel. Now we can create curves to form the face sheets. So go ahead and do that for the top and bottom, and we're just creating a simple panel here, rectangular panel. Now that we have curves, we can create our surfaces for the bottom and top face sheets, which can then be used to create the solid. And I'm just using the 2 curve option by selecting just the two opposite curves on each the bottom and top face sheet. And now you can see that it's not so bright. I'm going to go ahead and turn on a feature here that turns on all the directions of the light sources. So at the very bottom of the display options, if you turn on all 4 directions, then it gets much more clear and visible. Now that we have the light sources turned on, I'm going to go ahead and create individual groups or components for each of our parts. So we'll have the bottom face sheet, so let's call it FS bottom or bot, and let's select the bottom surface, click apply, and do the same thing for the top face sheet. Select that surface, and we can just post those two so we only have the surfaces displayed. And now we can create the solid core, but first why don't we create a component or a group for the core in preparation for that. And let's make sure it's the current group so that when we create the solid in the solid geometry, it automatically is assigned to that group. Just double checking that it's my current group. And now let's create the solid by using the to surface option, and we'll select the bottom and top face sheets as our surfaces and create a solid between the two surfaces. And now these surfaces lay directly on top of the core, and that's what we want. They're going to act as mid surfaces for our model. Now that we've posted everything, the two surfaces in the solid, it's hard to see those surfaces, so I'm going to change the color for those groups for the controlling the color by the groups, and I'm going to just change them to green so it's more visible. So I'll do that for the top and bottom face sheets. And the core, or the solid, I will just leave as the turquoise default color. Put it back in the center of the screen and rotate by the middle. And there we have our geometry. A random display issue that you may notice with Patran is that you can still see those orange lines at the bottom surface, and that's because in the geometry tab we still have those surfaces selected here. So if you delete them from the selection and then rotate again, they're gone. This is just a simple tip if you come across this problem when making your own parts. At this point we can start making material properties or the mesh. I'm going to start with the material properties first. And so let's go ahead and define our 2D orthotropic material for the CFRP that we'll be using in the face sheets. Selecting the input properties for this material, we'll need to assign values for the E11, E22, Poisson's 1,2, and the 3 shear modulus. As we discussed before, we'll just use the standard carbon fiber fabric or weave for this tutorial. So we'll have a Young's modulus of 70,000 for both directions because it's a weave, Poisson's of 0.1, and the in-plane shear modulus of 5 gigapascals or 5,000 megapascals. So let's input those now, again as megapascals since we were working in Newton millimeters. And so the in-plane shear, the 1-2 direction, is 5,000 megapascals, and for the out-of-plane shear we'll just use 3,500. These are just common literature values which are less than the in-plane shear. And then we'll click OK and apply, and now we've defined our CFRP material. Next we'll create the 3D anisotropic material for the core. So let's select that and just call it Nomex core. Now the trick to modeling honeycomb core without considering the actual geometry of the hexagonal cells is done by defining stiffness values for the directions relevant to the core properties. Here the 1, 1 direction is the x-axis, 2, 2 is the y-axis, and 3, 3 is the z-axis for the compression direction of the core. Next, the shear directions are 4, 4, which is the xy plane, which is not considered for a honeycomb core. 5, 5, which is the yz plane, which will be our ribbon direction of the core. And 6, 6, which is the xz plane, which will assign the shear modulus of the w direction of the core. This will be better explained once we enter actual values from the data sheet, so let's go ahead and do that now. So the core we chose is the -96, which is the density of the core. So we're going to need the compression modulus and the shear modulus for both the L and W directions. So the compression modulus, which again is the z-axis, is going to be assigned to the stiffness 3,3 value. So if we put that value in there, it'll be 414 megapascals. Next we have the L direction, which is the ribbon direction, and we've assigned that to the YZ plane, which is the long direction of the panel, and that will go in the 5,5 stiffness value, and that value will be 90 megapascals. And last we have the W direction, which is perpendicular to the ribbon direction, and that'll be XZ shear plane, which goes into the stiffness 6,6 value. And now depending on your part, you can put the ribbon direction shear modulus as needed depending on the actual ribbon direction of your part. So let's put the values in for each of the stiffness directions. So that was the compression direction, now the ribbon direction, which is again the YZ plane, and lastly the W direction, which is the XZ or the 6,6 stiffness. And now the last part we have to do is the other major stiffness directions. We have to put dummy values in, so we'll just use 1, and this is because when running through the solver, which is Patran, we will get an error saying not all property values are defined. So that's why we have to put 1 or a dummy value in those directions. So let's go ahead and click OK and apply, and now we've created both the material properties that we need for our entire model. Now we need to create the laminates for the upper and lower face sheets, which can be done using this laminate tool. So if we click on that, it opens up to a window where we actually define each ply of our face sheets. So let's call the first one the bottom, FS bot for face sheet bottom, and we need to actually add in rows for each ply, so let's go ahead and just make it 4 plies thick. So set that to 4 and click insert, and now we can define each ply of our face sheet. So selecting all the cells and selecting the CFRP material, it assigns those materials to each ply. Now let's just give an arbitrary thickness value of 0.32 millimeters. So again, you can select all the cells and enter 0.32 and click enter again, and you apply it to all, and let's just put them at a 45-degree angle. And now since this is a weave material, it'll be in the 45 and minus 45. And then I like to assign global ply IDs for each ply, so when I'm looking at results of the analysis, I can clearly evaluate one ply and I know exactly what ply I'm looking at based on the ID. And so I just arbitrarily chose some numbers here, and then I just delete that last row, which is blank, and there we have our bottom face sheet. With everything defined, later we can look at the laminate properties. So let's go ahead and click apply. Now let's do the exact same thing for the top face sheet. We'll do it exactly the same way. So 4 plies, all with 0.32 as our thickness, and all at a 45 minus 45 degree angle. I'm just going to renumber the global ply IDs so that I clearly know the 100 series is the bottom face sheet and the 200 is the top face sheet. Go ahead and click apply, and now we have both our face sheet laminates actually defined. And now using the show action, we can see the laminate properties. So select one of the laminates and show the properties, and you get our ABD matrix as well as other parameters of our laminate. Inputting more material properties would result in more overall laminate properties in this tab. And now at this point, we can either create the properties which we'll need to assign to the elements we create, or we can create the mesh, which is what I'll do now. And now we can create our shell and solid element mesh. Let's start with the bottom face sheet with a shell mesh, and we'll just use a mesh seed of an element length of 5, and so we'll select all the curves of the surface, and it automatically will create nodes at those locations. So now we can go to mesh, and with the quad element shape turned on and assuring that that group is our current group, we'll select the surface and click apply, and we will have our surface mesh of our bottom face sheet, and we will create and assign the properties after the mesh is created. So let's go ahead and do the exact same thing for the top face sheet. So a mesh seed of length 5, and select all these surfaces and create another surface mesh with quad elements. And lastly, let's create the solid mesh for the core. Again, a mesh seed of 5 will be used. And so the only edges we need to select now are the vertical or in the Z direction or the Z axis. So that'll make it 2 elements thick, which for our cases, our purposes is no problem, it's fine. And make sure to change it to the type as a solid mesh, because now we're making solid elements. And from tet we'll change to hex so that we're all square shaped elements. And the solid, we'll just select our one solid, and we'll go ahead and click apply. And there we have it. All our elements, our entire mesh has been created. So now let's go back to groups, and we can turn on all 3 groups, or post all 3 groups. And now I'm going to go ahead and reorganize the groups a little bit. I'm going to create a group of just all the geometry, since that is not really needed anymore. And then each of these 3 groups that I created, the core, the top face sheet, the bottom face sheet, I will put simply the mesh or the elements referring to that group in each one. So just a bit of group organization here, which is really important, not necessarily for this model since it's very simple, but once you have more complex models, group organization is critical. So now with our groups organized, we can create the properties and assign them to our shell elements and our solid elements. So let's start with the bottom face sheet. So we'll just post that group, go back into properties and create a 2D shell property, and we'll just call this face sheet bottom. That way we don't get it confused with the actual material we created. And now we need to change it to a laminate material actually instead of a homogeneous material. So let's go back and change it to laminate. So it's a laminate property, and now we'll get the properties of a laminate material. So for the material, let's select the laminate, which is the FS bottom. And our orientation for this example, we'll just use the global coordinate system. So just go ahead and select that. And now later you can create your own coordinate systems if for some reason you had face sheets at different angles and it didn't match up to the global system. It would be a good idea to create your own coordinate systems. And plate offsets are never usually something you want to use because it can create unwanted moments in your model, unwanted loads, and so I usually avoid using these, and I create the thickness of the panel or the model so that it goes to the mid surface of the face sheets, if that makes sense. So I add extra thickness to the core so that the core height is actually going to the mid surfaces of each face sheet. And now let's select the elements to actually apply the property to and assign the property to. And now we've created the P-shell property for the bottom face sheet. And so we're going to go ahead and do the exact same thing for the top. We'll rename it to top. And then in the input properties, we'll change the material name. And we'll leave it as the global coordinate system for the orientation. And now we'll select these elements and assign the property to the top face sheet elements. Lastly, let's create the P solid property. So change to 3D, leave that solid, and we'll just rename this to the honeycomb core. In this case, homogeneous is fine. And for input properties, we'll select our core material, which is again the anisotropic 3D material. And the orientation, again, we'll leave as the global coordinate system. So now we can select the elements that we want to assign this property to. And so they're 3D elements. So we'll change the selector to 3D hex. And we'll assign those properties, of those elements, this property. And now all our properties have been created and all of them have been assigned to our elements that we've created. The next step is to check the normal directions of our elements, and I always like to face them, have the normals of the elements so that they're facing away from the core, and this affects when you're building your laminates for each of the face sheet. It affects the stacking or the order of your face sheets. Now ours are symmetrical, and so it doesn't matter in our case, but when you have unsymmetrical stackings or something like that, the normal direction is going to influence the way the laminate is built. And so now I'm going to reverse the normals by going into Finite Elements, Modify, selecting those elements and clicking Reverse. And now if we plot those normal vectors again, you'll see that the vectors have reversed and are now, this is the bottom face sheet, and so they're now pointing away from the core. And this is just something I do to stay a bit more organized when creating the laminates, so that I know exactly, okay, I'm always building my laminates up away from the core, and so that the global ply IDs and the way I build the laminates is just a way to stay organized throughout the process of making the model and when viewing results. The last step that we need to do is to equivalence the nodes. So this can be done in the finite elements action equivalence, and this will remove all duplicate nodes that will have basically the phase sheets and the core should share the nodes to act as if they were bonded together, which it is in reality. And so we'll preview those nodes and then equivalence those to remove any duplicate nodes at those locations, so that when you apply boundary conditions and loads to the model, you don't have excessive pivoting in the model. So that wraps up this tutorial on how to create a finite element model of a honeycomb panel without modeling the actual honeycomb hexagonal cell geometry. Please leave a comment below if you have any questions regarding this tutorial, and leave a like if you found this video useful. Thanks for watching.